Hello everyone, welcome back. In this video, we will see about the best first search and its algorithm and one of the example. Hello everyone, welcome back. In this video, we will see about the best first search algorithm with an example. Best first search is an informed search technique which uses the heuristic. Heuristic is the cost from the node to reach the goal state. So it uses the heuristic information to make decisions about which node to explore next. So this additional information or knowledge allows it to find the solutions effectively, efficiently than that of the uninformed search methods. Uninformed search methods do not use such type of information. Best first search technique uses the priority queue. Let us understand best first search with a simple real world example. Suppose you are in a large mall and you are very hungry and also exhausted. It has 10 floors and you are on the ground floor. There is a restaurant on the ground floor and there is a restaurant on the 10th floor. As you are very hungry and you want food immediately. So what you do is you will choose the nearest restaurant. Though the restaurant which is far away from you serves your favorite food, at that time you want to reach the goal very quickly. So what you have avoided the optimal path. So your optimal path was the restaurant which would serve your favorite food or offers a better dining experience. Now you have given the priority to the closest goal or the most promising one. We want these kind of intelligent decisions to be taken by our AI agents. So let us see what kind of algorithm can we have for best first search. This is the algorithm of the best first search. Let us take a example of a graph to understand this algorithm better. We shall start with a graph. Let us take the first node A, then B, C and D as its successor nodes, and then G. In the best first search, we have heuristic values. So these are the nodes to which heuristic values are given. The heuristic value of A is given as 6, B is given as 4, C is given as 2, D is given as 5 and G is given as 0. Heuristic value is the cost from a point or a node to the goal state. Here the goal state is taken as G. G is the goal state and the start state is A. A is the start state and G is the goal state. In best first search, there are two lists. One is open list and another one is a closed list. So we shall start our search from the start state to the goal state. So we will see which path takes us to the goal state. So here let us write the heuristic values A4, A6, B4, C2, D5 and of course G is 0 because this is the goal state. From goal state to the goal state the distance will be 0. Initialization. So these are the heuristic values and each node has an associated heuristic value which is a numerical estimate of how close that node is to the goal. So A is 6 units away from the goal, B is 4 units away from the goal. There will be an open list and there will be a closed list. So as we are starting with the initial state, that is the node A, add it to the open list. So A comes in the open list and closed list is empty in the initial. Now let us move to step 1. Now we have to pick A from the open and generate its successors. So let us see what comes in open in the step 1 and what comes in the closed list in this step. So we have to explore the node A. The successors of node A are B, C and D. So we have to write B, C and D here. Write all these successors here. C is first because it has the lowest heuristic. The lowest heuristic among these three is of C. So we have to write C here, the lowest heuristic, and then the next lowest heuristic, and then the next lowest heuristic. And A is now explored. So A will come from the open list to the closed list. Among these three, the lowest heuristic value is of C. So we have to explore C here. C from the open and see that C has how many successors. G is the only successor which C has. In the open list comes B and D remains. In the step 2, we are not traveling towards B or D. We are discarding these two paths and we are taking only path C as its heuristic value is the lowest. C has the lowest heuristic value. So expand C now. When we are expanding C, G is its successor. So in the closed list comes A, comma C. Means we want to traverse from A to C. Now in the open list, B and D remains as it is. G is also added here. So the sequence will be G, B, D because G has the lowest heuristic, then the next lowest is of B and the next lowest heuristic is of D. So this is in the ascending order of the heuristic value. Now G is the goal state. So we have to stop here. Therefore in step 3, let us see what is in open and what is in the closed list. From step 2, from the open list comes G to the closed list in step 3. So A, C, G. Because this is a goal node, we have selected G in our path. So remaining is B and D in the open list. Final path will be the path which is in the closed list. Final path is from A to C, C to G. When we try to apply this algorithm, so if we compare the algorithm with our example, start with open containing just the initial state. So we are initializing the open list with the start state, that is A. Until a goal is found or there are no nodes left on open, what we have to do until, so pick them the best node on open. So what we are doing here is we are picking the best node, that is the node A from open, and then generate its successors. So what we are doing here, we are generating the successors of A. The successors of A are B, C and D. Here just we are writing it in the ascending order of the heuristic value. Then after initialization, we are picking the best node on open. So the best node on open is after A, B, C, D are the successors. When we are comparing this example with the algorithm, let us start with open containing just the initial state. So in the initialization, what we are doing in the open list, so we are initializing, we have an algorithm So here ends our example. So let us compare this example with the algorithm. Start with open containing the initial state. So we are initialization. So we are initializing with an open list, that is the start node A. After that, we have to pick the best nodes on open. So what we are doing, we are picking the node A. We are picking the node A from open, generating its successors. B, C, D are the successors. Then evaluating and adding it to the open. We are evaluating these successors based on its heuristic value. So based on the heuristic value, we are evaluating and we are putting it on the open list, and we are keeping C on the C. We are keeping C at the first of the. We are inserting C at the first of the list because C has got the least heuristic value out of these three. So C will come first, then the next heuristic value is B, and the next is D. And then for each successor, if it has not been generated before, evaluate it, add it to open. So what we have done this here. Generate its successors. For each successor, do the following. If it has not been generated before, evaluate it. So we are evaluating its heuristic value and adding it to the open list and record its parent. So these three parents are, so the parent of these three nodes is A. We have already recorded. And now what should go into the closed path? And the next one is, if it has been generated before, change the parent if this new path is better than the previous one. In this case, update the cost of getting to this node and to any successors that this node may already have. So it means that in this step we have to bring the node A to the closed list. So in this step we have to bring the node A to the closed list because we are sure to travel, because we are sure to keep A in the closed list in the final path. Next, step 2 is in the open list. Now among these three we have to select the best one as our search suggests, as the name of our algorithm suggests best first. As the name of our algorithm is best first search, based on the best heuristic value, we have to select the best node. So heuristic of C is 2, B is 4 and D is 5. So based on these three values, the best or the lowest heuristic the best and lowest heuristic value is of C. So we have to select or pick C. Again we have to go here C. We have to pick C because it has got the lowest heuristic value. Then C for its successors. Its successor is G. So we are sure to travel to the path so we are sure to travel to the node C. So this C will actually come to the closed list. So the closed list now is A comma C, and here we are picking C from the open list, generating its successor G, and evaluating and adding this to the open. So in the open list, G comma B comma D. So this is in the sequence order of the heuristic value in the increasing order. So the next step, step 3, as we have already, so now G is the goal which we have already found. G is the goal which we have found. Now pick the goal. Now pick the node G from open and now stop the search. This G goes to the closed list. So the closed list becomes A, C, G. In the open list remains B, D. So we are concerned about our closed path, which is the final path from the start state to the goal state. So the final path is A to C, C to G. So here we have seen how the algorithm uses open and closed lists to find the shortest path based on the heuristic estimates. We have seen the algorithm, we have seen an example based on the best first search algorithm, and this algorithm uses a heuristic to determine which node to explore next based on the heuristic value. And heuristic is typically an estimate of the cost or straight line distance to the goal node. Selects the node that appears to be the closest one to the goal at each step. It does not consider the overall path cost. It focuses onto the nearest or the most promising node, which leads to the suboptimal solutions. Let us know what is the space complexity of best first search. In the worst case, it is big O of b to the power of d, and time complexity is also the same, big O of b to the power of d. The branching factor, and d is the depth. D is nothing but average number of children or the direct connections from a node. So to a root where b is equal to the branching factor, that is the average number of children a node can have in a particular graph. So in this graph, the branching factor can be 3 and the depth is from the start node to the goal node. We have 2 edges, so d is equal to 2 for this graph. Best first search does not give an optimal path. Hope you have understood the best first search definition, its algorithm, its example. Comment, share the video with your friends, like and subscribe. Thanks for watching.